Yesterday we learned about two new concepts. Work, which is defined as the change in energy experienced by an object, and is dependent upon two things. What are the two things that work is dependent upon? What are the two things, in other words, that are necessary for work to be done? One of them is? You need movement, yeah. And what's the other one? The force, right. The force needs to be with you. And you need movement. You need a displacement. Now, when we write this equation as I've written it, W is equal to F times D, that assumes that the force and the displacement are parallel to each other. In other words, if one is going to the west, then the other is going to the west as well. If the force is to the north, then the displacement is to the north as well. What if they're not parallel to each other? What do we do if the force is to the west, but the displacement is 30 degrees off of that? How do we modify this, and how do we account for that difference in direction? Because in the end, we can't use this. Yep. Yeah, effectively what we're going to do is find a component, an x component of that, that force, and we're going to do that by subbing in cos theta into that equation. Really what it is F cos theta times D, but we just changed the order of it a little bit to look a little bit neater here. So, if the object is moving in the same direction as it's being pushed, or parallel to the way it's being pushed, we'd say our angle would be 0 degrees, cos 0 is 1, and our equation becomes F times D. If it's being pushed 90 degrees to the way it's moving, so it's moving this way and it's being pushed this way, then we would say the angle is 90, cos 90 is 0, and we would say then work is equal to 0, because none of the force that I'm applying is contributing to the motion, or contributing to increasing or decreasing the energy. And if the angle is something in between, let's say that I push it this way and it moves this way, then I need that angle in between the way that it's pushed and the way that it moves in order to get the x component of the force, so that I can figure out how much of that force is parallel to the displacement. That's work. That's change in energy. Work is a vector or scalar. It's a scalar, and the units for work are joules. Good. The units for work are joules. Good. The last thing we talked about yesterday was power. Power is almost the same thing as work, but it's a kind of an extension of work. It's a way of distinguishing not between how much work a couple things or a couple people have done, but rather how quickly that work is done. It's the rate at which work is done, or the rate of change of energy. So we're going to say for power, it's work over time. Now you see that if we increase the amount of time, Christian takes more time to shovel the driveway, then his work done will be the same, but his power output will be less, because the denominator of the time is bigger. If you do more work, then the power is going to be greater. All right, what are the units for power? Watts, or you could say joules per second. A watt or a joule per second is exactly the same thing. And power is a vector or a scalar. It's a scalar, yeah. Work is a scalar because energy is a scalar. Power is a scalar because work is a scalar. We did 3 questions for homework on work, and you guys all did them. That's good. I think you would have found that if you can do work, you can do power, right? Because power is just work, and then divide it by T. Sometimes you got to rearrange it and solve for something else, but in the end, generally what it boils down to is a work problem with a time on the bottom, on the denominator. Let's take a look at page 325. These are our 3 questions for homework. As I was walking around, it looked like there was a couple of people that had an issue with number 1, and 1 or 2 people that had an issue with number 3. Are those good if we go over those 2? Yeah? Yeah? Okay, so let's do both of those right now. The engine of a crane lifts a mass of 1.5 tons to a height. Oh, I can see the issue with that. What's a ton? What's a metric ton?
1 is 1,000.
Sorry?
1 ton is like 1,000.
Yeah, it's 1,000 kilograms. Yeah, a metric ton is 1,000 kilograms. So we're going to say our mass here in question number 1 is 1,500 kilograms, because it's 1.5 metric tons. And we're lifting it to a height of 65 meters. So we're going to say the displacement as we lift this mass, the displacement is 65 meters. Does that make sense? 65 meters up relative to where it started. My time is 3.5 minutes, but we got to convert that to seconds. 3.5 minutes multiplied by 60 gives me, I believe that's 210 seconds. Is that right? Yes? Okay, 210 seconds. And we want to find the power output. So we know that power is equal to work over time. We got the time. So now this becomes, literally, it becomes a work problem, right? You got the time. You just got to find the work. Now, this question is actually much like the example question that we did yesterday, which was the running up the stairs question, right? Remember, you guys ran up the stairs yesterday. We said your power output of your legs is work over time. Time, you just measured with your phones. The work, how'd you find the work yesterday? Work is F times D, but it's also delta E, or final minus initial energy. There's two ways that you can look at this one. If we're lifting this mass up to a specific height vertically, then we could say work is equal to F times D. And the force that I apply is M times G, so 1,500 times 9.81 times the displacement of 65 meters. When we do that, we get a work here, a work done on this mass of of 956,475. Okay, anybody else get that? Yes? So that's how much work I did, that's how much work the crane did in lifting the mass to this height using F times D. We're lifting it straight up, so the force that I have to apply has to counter gravity, so it's going to be M times G times the displacement. Now, the other way of finding work, though, is to say W is equal to delta E, and it's EF minus EI. The final energy would be potential, because it's at a height. The initial energy would be nothing, 0. So we would say the mass is 1,500, G is 9.81, and what's the final height? Oh, I start on the ground and my displacement is 65. My final height is 65. And look what you get when you do that. So either way you think of it, we end up getting the same value for work there, right? Force times displacement. Okay, force of gravity that we have to overcome times 65 meters, or we can think of it as change in energy, which is potential energy minus 0. The green way is the way that we did our activity yesterday. But you understand the way we did our activity yesterday, we had to do it this way because yesterday we weren't lifting ourselves vertically upwards to the top of the stairs, right? So we don't want to use F times D, because it's a little bit, it would have got us the right answer, but it's a little bit of a fudge to get the right answer because we weren't lifting ourselves straight up. Okay? That make sense? All right, so we got that work now. We take that work and we divide it by the time here. 9,56475 joules divided by the time of 210 seconds. And that should give us, I think, probably 4.55 times 10 to the 3 watts. Is that what it works out to be? 4.55 times 10 to the 3 watts. Now, they ask us to convert it to horsepower. I'm not worried about that. I'm not going to ask you on a test to convert anything to horsepower. But if you did convert that to horsepower, all we do is divide it by 750. Okay, there's 750 watts in a horsepower, so divide by 750. You won't have to do that, though. All right? The other question, number 3, says a tractor pulling a plow exerts a pulling force of 7,500 newtons over a distance of 3.2 kilometers. Don't want to forget to convert that. If the tractor's power output is 25 kilowatts, I don't want to forget to convert that either. How long does it take to do the work? Okay, what do we got here? We have a force here of 7.50 times 10 to the 3 newtons. What else we got? A displacement of, we say 3.2 kilometers? What is that in meters? What is that in meters? Yeah? 3,200 meters, or we could just say 3.20, leave it as 3.20, and then say a kilo is 10 to the 3. 3.20 times 10 to the 3 meters. 3,200, 3.20 times 10 to the 3, exactly the same thing. What else we got? What's this 25 kilowatts thing? Okay, it's 25,000 watts, or we could say 25 times 10 to the 3 watts, right? Or you could say 2.5 times 10 to the 4. What is that, though? What variable is it? W, P, D? It's P, it's the power output, yeah. And we're looking for how long it takes to do the work. What variable is that? Time, right. So if we know it's a power problem. We're going to say P is equal to W over T. We're going to rearrange it to solve for T. So the T goes up by multiplying, the P goes down by dividing, and we get W over P. Okay, we got the power. Once again, this becomes a straight work problem. Right? Let's solve for work, and then let's, instead of dividing it by time, divide it by the power. How am I going to find work? This is a pretty straightforward one, actually, to find work. How are we going to find work here? Yeah? Yeah, assuming the force and displacement are in the same direction, which they have to be here, otherwise they'd have to say something, then we would just say F times D. If there was an angle, then we'd say F times D times cosine theta. My force is 7,500. My displacement is 3,200. And my work is 7,500 times 3,200 gives me, holy cow, big number, 2.4 times 10 to the 7. All right, so there's the work. Just want to kind of block that off because it's getting a little cluttered there. 2.4 times 10 to the 7. Divide that by power. And the power was 25 times 10 to the 3, or 2.5 times 10 to the 4. And what do we get? Divide that by 25,000. 9.6 times 10 to the 2. And the units are going to be seconds, of course. So we say 960, or we could say 9.6 times 10 to the 2. Now, they got an answer as in seconds and in minutes. I'm not sure why they put that in minutes. Any of you guys converted to minutes? Why did you convert it to minutes? Because it was there? Because they gave it in minutes? Or? Yeah? Okay. There's no real good reason for that. I'm not sure why, unless a question expresses that they want it in minutes. How many minutes does it take? Then it's absolutely fine to leave it in seconds because that's the standard units. Okay, I'm not sure why they did that question. But I'd mark it right, even on a test. I'd mark it right even if you weren't asked for minutes, but because it's right. It's just an extra step, right? Good there?